My name is Kuansan Wang. I'm leading the group in Microsoft Research that produced this Microsoft Academic Graph. So today I'm going to take this opportunity to introduce to you our community outreach efforts, why we're doing this and what we want to achieve. And as many of you alluded, this is not the first time we do this kind of challenges. In the Wisdom earlier this year, we actually ran the first Wisdom Cup. And so the question is, why are we doing this? And so I am going to share with you mostly from Microsoft perspective, but as you can probably imagine, this is not just Microsoft effort. This is actually a society effort. We actually gather quite a few who's who in this industry. So from Microsoft perspective, I, as a research manager, one of the tough problems is how do I evaluate my researchers' outcome? And it turns out that this is not a trivial problem. In fact, the entire academic community is talking about this. And currently, they have discovered, in short, none of the existing metrics actually work well. And so a group of people, very big shot people, actually talked about this for like 5 or 7 years. And then finally, 2 years ago, they congregated in San Francisco. They decided that the current situation can no longer sustain. And after that congregation, they issued something called Declaration on Research Assessment, or DORA. Unfortunately, this keyword, if you type into search engine, it shows you a cartoon character, but Dora the Explorer. But this is actually quite serious. The people behind these are actually who's who in the research community. They include the publishers of Nature, the publishers of Science, the publishers of National Academy of Proceedings of the National Academy of Science. These people, they are, if you look at the academic graph, you would know that we computer scientists, even though we are very productive, we only account probably 10% of the graph. The rest of the 90% are these people. But the gist of it is what is this. So currently, oh, wow, I apologize for this is not showing up very well. But so basically, the research community, as you probably know, have quite a few metrics floating around, evaluating either researchers' productivity or how good the research work is. The most famous one would be H index, which is supposed to evaluate how productive a researcher is. The foundation of H index quickly is you plot a histogram based on the number of papers that you have and the citation count you receive. And so typically it looks like a curve, like exponential decay curve. You take a diagonal thing, and the intersection is your H index. H index has been around for a while, and it got popularized by Google Scholar. That's the matrix. That's the metrics that Google Scholar reports. So quickly, if you go to a lot of universities and ask the faculty, how do you determine a promotion of faculty members? A lot of them will say they will ask the H index. Right? So it's quite influential, but it has problems. In the declaration of, in the DORA, that documents, one of the obvious problem of H index is does not discriminate the citing source. So if you are a professor having a lot of students and they all publish papers, they cite your thing, your H index is going to be very high. Another thing is Google is actually quite an amazing company. So if you just put anything out there on the web, they will find it very quickly. In fact, in our group, we did a very simple experiment. We just put our talk, like this talk, and add a reference section at the end, and refer all your stuff out there, convert the PowerPoint slide decks into PDF, and put it onto website, our research.microsoft website. Because research.microsoft.com is a very high page rank sites, it got indexed very quickly. And it looks, it's a PDF, and oh, there's a section called references. It looks like a paper. Immediately, all the items in the reference sections got counted as your citation. And immediately you see your citation count jumps, and as a result, your h-index. So it is a very well-known problem, and Google is doing this very well. We actually have evidence that within 2 hours, they can actually update your citation count. This is one known problem. H-index, it's great. It has a certain attractiveness. It's easy to compute, easy to understand, but nevertheless, it has a drawback. The other one is very famous, especially in Asia. It's called journal impact factor. It's dated back to 1970s by Eugene Garfield. And then currently, after he invented this matrix, now currently the stakeholder for it is Thomson Reuters. They actually using this one to assign the impact factor for publication venue. So H-index, the problem of H-index is it does not discriminate the citing reputation of citing sources, right? So a lot of universities, and even funding agencies, they decided, okay, let's do a compromise. Let's only count the number of papers you publish got accepted in the high journal impact factor journals. And in fact, some government agency in Asia would actually use that to determine the bonus for the government agency researchers, or even use it as a metric for determining who should get a grant or not. So the problem of this approach is, of course, they did a very elaborate study. And by the way, the DORA signers, they are all publishers from high journal impact factor, like Nature Science, Proceedings of NAS. They found this is actually a problem because when they look at their publications, not every paper should be treated equally. Even good journal, high journal impact factors journals would have bad paper, meaning it should not be treated the same way. They are actually, and also the citation patterns also different. A good way to get a lot of citations is to write a tutorial or review papers. But in many cases, when you want to evaluate the research outcomes, you actually want to know how original the work is, not just the review, right? So this journal impact factor is yet another interest. It's too raw. It's aggregate metrics, too raw. So then we all know PageRank is trying to solve this problem, and I'm going to touch about this issue later, right? So these are the first beef of the DORA. The second one is the alt metric. So now more and more we are living in a digital world, in an online world. We are not just publishing papers. We actually we also contribute to the community in all sorts of different ways. Some of us in the industry, we ship products, or we produce data sets, or we actually give talks, lectures, so on and so forth. How are these being measured? They actually take time, and a lot of you in the universities, you teach courses, you write textbooks. Textbooks get a lot of citations, but how about other activities? And so a lot of funding agencies, like most recently is NIH, US NIH, they started asking the question that maybe we should consider something called alt metrics, alternative metrics, that take into considerations all these quote-unquote modern online activities into the contribution of your research outcome, right? But so how do we do this, right? And the final problem is if you read the DORA, they actually include a open letter to Thomson Reuters, let's say the Avenger of JIF, saying that your data is opaque. We don't know if you are doing the right thing, and thousands of researchers are being evaluated based on the metric you published. We are inherently scientists. We would like reproducible results. Can you possibly open your data to us so we can actually look at it, massage it, and see if there are anything we can improve upon it? I don't know if you know, the pressure on Thomson's routers is so hard, is kind of large. So Thomson Reuters decided to sell the business. As of July last month, they sell the Web of Science, that part of business, to 2 hedge funds in Asia. So nobody knows what will happen next. So it's an interesting development to watch. So a group of us are also talking about this. And so we decided that why don't we're scientists, we are data scientists, we're good with data. In the case of a lot of us, we actually have a means to gather the data. So why don't we take the first step to see if we can actually make some contribution to the entire academic community towards this. And unlike other data sets, which comes with all sorts of privacy concerns, we researchers, we all want to know, everybody know that the good work we have done, right? So this is actually anti-privacy concern. We actually want everybody to know what we have done. So it looks like this is a great data set that we can start collecting, building, and then use it as a common platform for we data scientists to work together, together. So this is and it's very easy to find a like-minded person. In fact, this activity has gone through a while. And so this is our core belief. We believe the method to compute, evaluate research assessment should be open. It should not be a black box. It should be very transparent, and you should know what you are being measured against. Whether you are a faculty looking for promotion to a tenure, or you are a grad student trying to find your first job. There inherently is a way, something is measuring your research outcome. We believe that algorithm, that methodology should be accessible and be known to everybody, right? And similarly, we also believe the data going into that algorithm should be open and openly accessible as well, all right? So this is actually what the basic belief. And just what we had in the previous session, this data set has obviously applications beyond research assessment. You can use it to predict trend. If you're grad students, you want to know in a few years what are the hot topics. That's probably one thing that you can do. Or you want to know that how come KDD becomes so large. You remember it used to be a workshop. And you can probably see what is the patterns for success. Maybe you can learn some lesson out of it, and so on and so forth. And you saw this morning how showed us a graph. It turns out that our publication record actually track our socioeconomic status very well. And we actually, for the first time, have evidence that wars actually set our civilization back. So are there any more trends, more interesting story that we can tell? So we would like to have a common platform, common society that we can actually brainstorm and actually cross-pollinate the related efforts. As I alluded, the like-minded people are a lot. They actually scatter around many societies and disciplines. From Triple AI, there are quite a few workshops in this area, in the machine learning and AI, and dub, which is very cross-disciplinary effort. There are certain activity over there. JCDL is the Digital Library and Information School. People, they are the granddaddy of the cytology and bibliography research. And of course, us, the data mining, data scientists, data science people, or the IR, the SIG IR, and the big data community. And then also, because a lot of time you want to read the papers to appreciate what people have done. And so actually, the ACL, the Computational Linguists Society, also for that. But if you did a literature research, you will find how to measure research input actually is published in every discipline. I can find physics, Journal of Cell, doing biological thing. They all have papers. They digress from their day job and talked about how to evaluate these things. So it doesn't take, it take a while, but it doesn't take much to convince a lot of people to join the foray. And so officially, so finally we decided that we wanted to do something together. So just a little bit a month ago, July 15th, we all congregated in Redmond, Washington during a Microsoft research event called Faculty Summit. So we decided to gather together and figure out how to organize ourselves. These are the participating the members in that inaugural meetings. I hope you can see that this includes a big chunk of who's who in this community. We have a Tsinghua University who has generates the A-minor, is one of the largest social graph for scholars. We have a Chinese Academy of Science. They are actually from two institutes, from Computer Science Institute and National Science Library. We have Scienceer. It's probably granddaddy of search engine, of paper search engine. The Penn State is, oh yes. So Professor Lee Giles is actually there. We have a data lab from University of Washington. It's just across the lake from us. So their participation is very straightforward. And Easy Chair, it's a conference management. So if you submit to KDD or to other conferences, you probably are asked to submit papers over there. They also can actually help, or actually can have a lot of synergy, like disambiguating authors and institutions, so on and so forth. Elsevier is largest academic publishers in the world. Currently, they are being perceived as a bad boy in the industry because they are actively enforcing their copyright laws. So you cannot put your papers on the web without asking them if you the agreements as such. But they do have a business consulting funding agencies in the world to evaluate their research grants, how well they are spending money on research grants. Also, they are also interested in seeing what we have to do. National Australia Universities and Allen Institute of Artificial Intelligence, they have this Semantic Scholar. It's a new search engine for searching papers. It's quite cool. Their specialty is machine reading, so they actually train the machine to read the papers and can offer you better citation or related recommendations, so on and so forth. So we are very glad that the Semantic AI 2 is here. Shanghai Jiao Tong University, this is a university that produces its own ranking for the institutions. We are also, of course, they are interested in joining with us. University of Arizona and the rest of universities are actually just like-minded people. And not all of them are actually computer scientists. So for example, Vanderbilt, the participant from Vanderbilt is actually from the economic community. They would like to know that how to model this math and things like that. So in this inaugural meeting, these are the key outcomes. So we're going to merge. We're going to produce a graph that is like a Wikipedia. Also, we are going to attach a open data license, put it out there. And initially, it will be the merged graph of Microsoft Academic Graph and the Tsinhua's A-minor, which we already cross-linked together to create a big graph. And so we are going to put it out there as the initial set. And this open data license implies that everybody can use it. Everybody can grab a copy, use it, as long as you have a proper attribution to the source. So we don't care if you are just doing a research or you are actually a startup trying to create a business on top of it. That's fine, based on as long as you put proper attribution. And similarly, we also have a contribution mechanism. So just like Wikipedia, you can actually go in and say, yeah, this bunch of data is wrong. I want to contribute back to the graph. And the data license is also the same one, ODCBY. So it operates like Wikipedia. Currently, it only has what you already seen. It's metadata of all the publication records and some of the social records from Tsinghua University. But recently, we just overcome a legal constraint that we have a means to provide text data that is considered copyrighted material to the community. So if you're doing text mining or you're doing NLP, party on. Right, so we are going to have a regular board meetings, and we decided that we are going to have an annual face-to-face meeting. We have some discussions as should we attach ourselves to a existing venue or we create our own, and if we want to attach ourselves to existing venue, which one to go, KDD or something. In the end, we failed. This field is a multidisciplinary enough that either going to the AI or going to data science is probably a little bit, is probably not fully realizing its potential. So the current decision is we are going to congregate at conferences, which is quite nice because it covers systems to NLP, text mining to data science, and recently they collocated with digital health and all sorts of other events, so we can just attach ourselves to it, right? And all this is based on, and you heard about this morning, there are people reporting that the big data, the data is getting big, so you need to download it. It takes a while to download it, and once you download the data sets, you need to maintain a cluster. You have to make sure it is running. Microsoft decided to donate. So for students, if you want just to do some rudimentary research, trying to put a large cluster out there is probably kind of challenging. So Microsoft is donating for academic institutions and students free access to the cloud computing infrastructure. So you can just develop your research agenda in the cloud and check the status on your iPhone or iPad or whatever. Kind of nice, right? So currently the group has a temporary URL called openacademic.ai. It's not .org because it is taken, but because it has some artificial intelligence element in it, so .ai seems to be adequate. Right now, it's actually temporarily housed under Microsoft's website, but eventually it will be separate out from its own. And there's a Microsoft's role is served to this society as a secretariat. So you can contact us through OAS, Open Academic Society Secretariat at Microsoft.com. Right. So that's the data set. But how about the methods we talked about? So we have an initial contribution from Tsinghua and Microsoft to donate a large graph. And whatever we do at Microsoft, we are going to continue evolving the Microsoft Academic Graph to have more data. In fact, if you remember that Hao's graph this morning, we are very productive. Our number of papers is growing exponentially. What he didn't say is the slope of that thing is 0.8%. So currently we have 150 million in our graph. 0.8% translates into 1 million papers a month, roughly. 1 million papers a month. But the graph, as you know, the biggest part of the graph is not the papers entity, but the citation relationship. And citation relationship grows polynomial with paper. So it's a huge data set, and we have a regular, I would like to say weekly update of graph to keep up to date with the, to continue to grow the graph. And those are going to be available through our API. But for a lot of you, when you are doing the research, you actually want a frozen data set. So that would be our snapshot release, just like what we did for this KDD cup. All right, so these are, right, so that's the data set. How about the method? So in that graph, you probably noticed there is something called log prob. It's a score that attached to every entity. And that entity, that score is actually the initial. We are going to contribute the Microsoft, the way we are I think someone asked about that question. So I'm going to contribute this to everyone today, how we actually end up with that score and use this as a starting point to engage with you, data science community, to further improve that thing. And what is that score? The score is actually what we in the search engine community call static rank. And I'm going to, for the rest of this session, I'm going to go a little bit in detail in here. Hopefully, this is afternoon, so you have enough coffee, so I hope I don't put you to sleep. But the design goal for that is actually to address the drawback that DORA document has mentioned. Right? So the idea, so first, of course, we want to have a single number instead of a bunch of numbers. You don't know how to put them together. You want to have a single number, and it's easy to compute, just like a H index. It's very straightforward, very easy to understand, and once you have the data, it's easy to compute, right? Even though a lot of people are saying that this is actually misleading, you should actually read a paper, but in many cases, you just want a number as a starting point. Right, so that's a design goal. And we just talked about H index. The drawback of H index is not discrete, is not distinguishing the citing party's reputation. So we definitely want to avoid that same problem. So we consider the reputation of the citing party. And we also talked about journal impact factor is too raw a metric. It only talked about journal, it's not talking about individual research work. So here, we actually want to per entity score. And it turns out that actually I didn't put it on slides, but it's not just paper we want to evaluate. We also want to evaluate each author, each institution, like this KDD cup, eventually, and also different kind of conferences and journal to see how we actually measure up against existing thing and to engage with the community to see if the results actually are actually making sense, right? And temporal dynamics, one of the problems with the H index is also based on the citation count. The citation count in there don't necessarily age, or you do aging in a very ad hoc way. You just say a particular window chunk, right? But for some applications that may be fine, but most of the time it's probably not good enough. Recently, deep learning or AI is enjoying a renaissance, and a lot of classic paper actually dated back to 1980s. So how you cannot just put a Windows to it, right? So obviously we wanted to have some good way to handle the temporal dynamics of the citation behavior and so on and so forth. And we want to take advantage of heterogeneity. One of the problems with H index or the JIF is they all consider single entity. Journal impact factor is only considered journal. But we actually have all other things. So hopefully we can look at the conference, right? We all talked about heterogeneous graph. This is a heterogeneous graph. So we definitely want to take advantage of that as well. So the basic ideas in the graph is a probability. So the idea, the assumption here we make, well, in order for your research work to have impact, it first at least has to be known. If nobody knows your work, how can that work has impact? So the idea is that can we estimate the likelihood of a particular research work or research institution eventually will be universally known or popularly known. This is kind of you go to the first day in your grad school, you go to ask your advisors, what paper should I read? They will probably, yeah, these are the papers everybody reads, or who should I follow? What conference should I pay attention? Yeah, these are actually famous people are doing. It's that layman concept we want to model, and we model it as a probabilities of eventually that everybody would know, right? So it's a very simple score. It's a likelihood, how likely. And you can also think it another way. If you cut the graph, all the edge in the graph and put a node in a big jar, and you randomly pick a node out of it, and the probability is actually corresponding to how famous they are. So the balls are not of the same size. Their size is actually corresponding to their popularity. Then the likelihood of they being selected, randomly selected from that jar is this probability. So that's the likelihood score, log probability score you are seeing in the graph that we released. Another thing is the partial observability, right? So the ideal thing is we wanted to estimate whether the paper has been known or be read, but we cannot exactly directly observe that this paper has been read. So we have to find a lot of proxy. The most confidence proxy is it's being cited, assuming that the citing author actually read the paper to cite the thing. But nevertheless, just like in a search engine, the thing being clicked means at least people find it's promising versus the result that people just go and skip over. So that's actually one signal, one definite signals that we want to use. But we have to recognize simply because a paper is cited doesn't mean it's the only way that we know that only times we know they are being read. So there's some latent vector that people just read a paper, feel inspired by it, but when they write a paper because of page limits or whatever, they didn't put it in citation. So we cannot take the citation as a face value. We need to do some additional techniques to compensate it statistically. All right, so that's actually the partial observability thing. And finally, this likelihood obviously has to decay over time. People talked about it this morning. If a paper does not receive sustained attention, obviously the likelihood score should drop. But if you just take the citation counts, it doesn't work this way. Older papers naturally will have more citations counts, have higher citation counts. It's not fair, right? Especially to new papers. So we want to do that as well. So how do we work? Well, doing big data processing, the important thing is you want to make sure your algorithm is sound, is rigorous. Otherwise, you don't even know how to look at the result and see whether there's a bug in your program or is actually the fundamental problem of the algorithm itself. So what we did is we go back to the mathematical framework. And it's called Perron theorem. It's actually very old. It's actually before World War I. Right, and this thing actually underlies the random walk that is being used today in PageRank. So I'll quickly take you through this, and you will know that why we did the thing this way. So imagine let's first start with the homogeneous graph. Imagine you're given a directed graph, and then there's a number attached to each link, indicating how strong that the link is. And for our purpose, you can say that how likely from one node will be you will discover the next one. Just for and mathematician call it affinity matrix. So. And you can imagine that you are given a square matrix where the Aij is actually a link indicating how likely node J would refer node I. All right? So, and there's the mathematician called Perron actually proved that, oh, okay, so if this matrix is a positive matrix, there's some great properties happen. And there's a lot of properties. I just singled out the one that we wanted to use. It actually says that the eigenvalue of this matrix is the largest eigenvalue exists and it's unique and it's positive. 3 things. So that matrix, you can actually diagonalize it, and the largest eigenvalue guaranteed to be unique, and is guaranteed that it is positive. All right. So what is the significance of this outcome? The outcome is when you keep doing the power law of the matrix, the matrix, you can say this is a unitary matrix and a diagonal matrix with the diagonal elements are all eigenvalue and the inverse thing, right? So you take the matrix operate itself n time. Eventually, the unitary in the matrix will cancel out. What you are left over is the diagonal matrix raised to the nth power, which would become the eigenvalue raised to the nth power. And therefore, the largest eigenvalue eventually will dominate that diagonal matrix. Everything else looks insignificant. And so what happened then is, if you take any vector and you keep multiply matrix to it, eventually you all converge to the largest, to the dimension that the largest eigenvector points to, regardless your initial state. It's amazing. You can randomly choose whatever starting point, and you treat the A as a transition matrix, and then you just keep operating it itself. It guarantees, the mathematics guarantee that you will converge to one thing, and one thing only, and that's the eigenvector. And so if we normalize all these eigenvector, interpret this eigenvector as probability of being visited, and then x, we also treat the x as the initial probability of you starting which whatever node you start. What happens is that regardless, this mathematical theory basically says, regardless of your initial prior is, as long as you apply this matrix on yourself alone, you will find out eventually how nodes are relatively important to each other. Right, so it also indicated a very straightforward implementation. You just random walk. Let's randomly start with something and then walk around. As long as you walk the graph based on the affinity matrix, you're guaranteed that you will converge to the right thing. And the convergence speed is exponential, so it's darn quick. So this is actually the base of random walk. It's the base of Eugene Garfield 1972's general impact vector. It's also the base of all sorts of eigenvalue-based eigenvector and thing. The math is actually very old, more than a century, right? But the condition for it to hold is the metric has to be positive. And if you look at our graph, a lot of, remember, if you compute the affinity just based on the citations, you will find a lot of nodes actually don't have citation to each other, which means the matrix has a lot of zeros in it. In fact, it's a sparse matrix, right? Google actually tried to apply this. They have the same problem. They are given a web graph, a graph of web documents. They wanted to know that which are the important web pages. And so and Google obviously is not the first one trying to use the random walk to solve the problem. But they are the first one to recognize how to deal with this imperfect world that the affinity matrix is not positive. And so, and if you think about that, most of the time the naive treatment is if you don't see the citation, the entry is 0. But 0 in here means that it's impossible for a node to go to the other node. That's a probability 0 events. But in fact, what we are dealing with is we haven't observed the influence of a node A to a node B. So we want to, if you're just setting them to 0, you are not distinguish 2 things. One is non-observed events. The other is that event is observed, and we know it's probability 0. Right. So Google's contribution is they introduced some statistics method called smoothing to deal with it. As Particularly, what I did is something called back-off smoothing. So what the idea here is that, well, at the time t, basically, I'm not just following the random walk graph all the time. There is a certain probability I actually want to teleport it to a random node to restart the walk together. So they introduced two things. One is the lambda. In the paper, they call it damping factor. People also call it teleportation probability or whatever. The other is U, when you want to transport. Where do you transport to? And in the paper, they say, yeah, we don't know. Let's just assume that uniform distribution, right? And how about this damping factor? Sergey and the original Google paper saying, well, we observed people typically follow hyperlink 6 times before they actually stop following hyperlink. And therefore, we should choose one out of 6 or 0.85. And that's the number. Seriously, I'm not kidding. So that becomes the magic number. And it turns out that a lot of people follow this and applying to physics journal and things like that and say, well, no, yeah, in physics, we don't do that. We actually only follow 2 papers. And so actually, you will find a lot of papers just debating how do you choose this damping factor. I'm not kidding. Very high journal impact factor paper just debating how do we choose damping factor. And also the U, uniformly selected, is that a good idea? Believe it or not, a lot of papers say, yeah, we should choose it this way, choose that way. Ideally, in the end, it's all empirical. There's no way to prove that rigorously, right? So but nevertheless, it's the first work that make this random walk recognize that the real life, when you apply this a random walk idea to the real life graph, you need to do some adjustment. What we did is, instead of doing this back-off adjustment that requires these magic numbers to be tuned, we did another thing called discount smoothing. Instead of saying that, okay, all the non-observed event has a 0, we're saying that, no, they are not. Why don't we just let the observer event added up to something less than 1? And have the rest non-observed event entry share that the remaining probability. And by doing so, the entire A becomes positive again because the lowest floor is that epsilon, which is a positive number. And so, yeah, everything works again. And implementation-wise, it's equivalent to PageRank. But theoretical, it's very different. It's easier to explain. And the discount smoothing, how do we do the discount? The epsilon basically is the probability of running into a non-observed thing. So how do you do that? Well, cross-validation. You just artificially separate your graph into 2 parts, and to use the first part to see the second part, how likely, how many things are in the held out data that are not in your thing, and then you can compute the likelihood of running into something you are not expected, and that's what we did. For those of you doing language model, you will find that this is very straightforward. This is called OOV, out of vocabulary probability, and we just borrow that over here. All right, so another thing, so in real life, we are not just following the citations. We're not discovering new papers just followed by citations. Sometimes it's because of our field. I know that I did a good job following the field I'm interested, or I actually follow authors. If this is a famous author I like, whenever they publish papers, I want to make sure I read it. Or like KDD is an important conference in my field, I will make sure that I read it. So we actually have multiple ways to discover a new paper and to have the paper known. And so there are multiple factors to put in there. And most of the time, sometimes I do keyword search to discover new papers. So these are additional factors. And so we model it as a different type of the node in the graph. We do random walk. And so basically, we're saying that the assumption here is that we can actually model it as a very simple statistics tool called mixture distribution, which is a weighted sum. This A now becomes a particular entity type on the other entity type. And the Vy is actually how important that particular entity type is. For example, if we're trying to do X is author, is paper, Y is author, then this AXY is how likely you will discover a particular paper by that author. So very straightforward, just like a citation. And this is a mixture distribution, so literature abounds about how you estimate this parameter. But let's get this later. So finally, quickly, how do we deal with temporal thing? So the simple assumption here is the probability the temporal dynamics can be modeled using a simple autoregressive process of order 1. This morning, a speaker also talked about this exponential smoothing. Same idea. Basic idea is given time t, the score is basically just a decaying factor of your previous one plus this mixture thing of the current one. And so now we are ended up with several free parameters, the alpha, the time decaying factor, and all this W, which is the mixture components, how important they are affecting each other. So how do we estimate those? The good thing is, so now this is the part that we make the assumption. We believe one thing. The assumption we make here is the new citation counts are sort of related to how famous that paper is. If the paper is actually very famous, it should receive citation. But they are not necessarily some linear relationship. The way we are modeling it is we model it as a noisy channel problem. How well known, how likely this paper will be discovered would actually kind of attract the citation, new citation you receive in the maximum mutual information way. Right, so what we are actually ended up doing in estimating these free parameters is the following. We take the recent, we pretend we only see the graph up to a certain time ago, like 3 years ago. And then for each paper, we accumulate its citation count of the less than three years, or actually 1 year or 3 years. It doesn't really matter. So now we actually have the citation counts for the papers, for the new papers. And we assume that count is tracks is a sum is it's a informative. It's a outcome of putting the likelihood through a noisy channel, and so we wanted to maximize the maximum mutual information of that. And in statistics, this is called MMI estimator, and so we actually use MMIE estimator to estimate all this probability. And this is a well-defined problem because all the W, it has its mixture coefficients, so they all positive, they sum up to 1, and so is alpha. So you just dump it to what are your numerical tools like GBFS, then you can solve it. And so that's actually how the scores are ended up in the graph. All right, so mutual information estimator on all these seemingly reasonable assumptions, I hope. Right, so what is the outcome? We actually find out that we didn't assume the mixture coefficients vary over time. So one of the things we test is to see how stable it is. And we actually validate on several graphs, assuming we look at a different time and compare the mixture coefficients. If they vary a lot, there's a problem. But fortunately, it doesn't. It looks like this. It turns out, other than citation itself, the rest of the factors look like this. The second important factor is affiliation. Where is this paper published from? If it is Google, probably a lot of people read it. From a famous institution, its chance is being read, chance is higher. The second one is where it is published. Makes sense, right? People tend to read the paper. Wait, what happens to these numbers? Yeah, anyway, my PowerPoint skills are not too good. But we can publish the coefficients over there. So the venue and field of study, they are roughly the same, meaning that it's kind of reasonable in the sense that you actually read the conferences follow or you follow your fields very closely. And key phrase is actually, it's play a factor, but it's not as big as what we think. And so these are the W, the mixture coefficients. The alpha, the time decaying factor, we talked about that this morning that this probably has to be fine-tuned based on different fields of study, different fields. We didn't do this, so we just used one for everyone. And it turns out that the half-life, it's an exponential decay, so half-life roughly is 6.5 years. Right. All right, so how is the result look like? We actually publish the ranking on a website that Alex is going to demo at the booth. So we compute this thing and then create a search engine of it. You can come to Alex's booth and try it out.
Or you can log props
from the graph, yes. And so you can do like in data mining, who are the famous institutions. Based on this score, we have a institution score listing about it. Who are the famous authors? Then you can do more fine-tune about it. And so this is these are the methods. We put it out. We are going to write a publication out of it. There's a lot of details that obviously can use a lot of improvements. As I said, this is actually a starting point for this open academic society. We want to engage the whole research communities to work together, and everyone is welcome to join. So this is a quick overview of this society. And we hope in a few years this can be as well known as Wikipedia, and I even hope that some of you can become our editors, our contributor. But with that, I am happy to take questions. Yeah. Yeah. So Jie is a little late. So would you like to come over as well? So he's also one of the founding members.
Oh yeah.
You wanted to
Thank you very much for the introduction. So I just one comment, okay. So the color is very unclear, right? I don't think you guys can see the text here. Okay.
Yeah.
So, okay.
Anyway. I apologize for my PowerPoint skills.
Okay. So do you have any question about that? Actually. Yeah. Yeah, please.
So my name is Sharon. I'm from the University of Science Institute. So it's a very exciting development, and because as someone who struggles constantly with bureaucracies from third-party data set like Web of Science and things like that, and well, sign me up.
Oh yes, you can actually sign up with Alex, or send that email. Yeah, right. Or send that email to OAS-secretariat.
Okay. Yep. So the check here is that I'm coming from computer science, right? So I've been trying to. Some of our computer science friends has been when we collaborating with people from library science and so the more traditional science people, there being a resistance using these kind of open data.
Mm-hmm.
Well, it's not like they like the openness, but it's like they rely on their publications, their industry, on what they call the quality of the Web of Science and things like that. So it's very difficult to publish in their field using these, I guess, newly established data sources. I guess. So I guess my question is, how do you see you guys moving forward in terms of how can maybe us right in this fight and promoting what I think one of the biggest advantage you guys have is this reproducibility issue that you pointed out. Because I think it's being more and more sort of pronounced, and people are thinking it's very important to be able to do something like that. Because currently, I'm a big sort of challenge we have is doing things like entity resolution, also disambiguation.
Mm-hmm.
My frustration with them is that whatever I do to their data source, get their approval, and I may not share even. People just reinventing the wheels all over again.
Mm-hmm.
So I'll leave it to you.
Right. So the question is, how do we talk to people from library science community? That's actually a very interesting question. We computer scientists like to use advanced data mining skills. That community, to me, my personal experience is talking to them, they first look at the data and say, this is wrong, that is wrong. So it's item-based debugging. And they are very good. They are very meticulous in handling their data, and they are not afraid of using manual libraries. But what I found out is we have a common language, and that's called statistics. That's a good thing. It's just that a lot of time they use statistics in a more traditional or majority of publication way. They know p-value and things like that, but not to the extent of how we use it. Bayesian inference, that kind of thing. But I think this is actually a very encouraging thing is now we have a common data set, common platform. We can try to learn each other's language and try to speak the same language. And one of our potential partner is actually from National Science Library. Yes, I totally understand what you're talking about. Yeah. Jay, do you want to add more?
Okay, so I guess the point here is we just want to make everything more open, just like an open community and open data, and also open community, open platform. So we also welcome for example, the people from library science and to join these efforts to work together. And also we can see some kind of trend that in library science they are also become more and more open. For example, the publication papers they have open access. And also, they also want to, for example, archive, they just publish everything to the research community and also, yeah, somehow like that. So we want to build some kind of open society. Yeah, you want to add something?
Yeah, exactly. So, and in fact, I mean, I think one of the issues around what's happening with the science community is the fact that Thomson Reuters, Web of Science, has become the de facto standard, but they do gate who can get access to that database, and so it does sort of limit the audience of who can participate. If you take the Microsoft Academic Graph, for example, you will see a lot of examples in there where we have done entity linking across the authors, across the affiliations, from keywords into field of study. But we try to provide both the original raw values that we're extracting as well as the linked values. And so this is another instance of a place where we'd love to have the community come in and improve on the approaches that we're taking, and look at the linking that we're doing from raw affiliation name into our sort of canonical lists in there. So we're trying to address lots of different problems at the same time, not just the analytics problems. Any other questions? Yes.
So do you plan to have kind of, to merge the data sets that are available, like, CiteSeer and A-Miner and so on, or do you see them that as standalone data sets?
Yeah, actually, as already Kuansan already mentioned, actually we just
Sorry, got the mic runner here.
Okay, so just as mentioned by Kuansan, actually we already collected A-Miner data and Microsoft data together. So we will just open the data at our website very soon. And this data basically will contain publication data and also author profile information, for example, affiliation and position, and also some other statistical information. So for research.
Right.
Yeah.
And with regard to CiteSeer, yes, Professor Giles and his team are actually working with us. So if you notice that one of the graph that one of the advantage the Microsoft Graph has is our front end is actually a web crawler. So we discover new URLs very quickly. And the strength of a CiteSeer, or to some extent the semantic scholars, the Allen Institute, is once they get a hold of the text, they do more in the text mining and extracting. So for example, like CiteSeer, they were extracting figures or all sorts of things, right? So, but because they are not operating a web crawler, so they not necessarily know where papers are. And we actually have this capability to tell them, hey, these are new papers. By the way, their PDF can be downloaded from here. And so this is actually a way that it's examples of how members in the society collaborate with each other. We are leveraging each other's strength. And in fact, one of the purpose of this society is if we can we can leverage each other's efforts, and then we can avoid the duplication and redundancy. So please join us and let us know, and then so we can actually work together. Yes.
So, can you also say when and where is the workshop? I think it's all day tomorrow, but I think for the other people, like, when is the
Next workshop?
No, I'm sorry. The place you're going to represent about the.
So actually, at our booth down on the ballroom level, I think directly underneath us, starting at about 9:15 tomorrow, through all the breaks and lunches tomorrow and Tuesday, and then Wednesday morning. Come to the Microsoft booth. There's 3 kiosks in the booth. I and Hao and other people will be there I just signed you up. So.
No, he's flying.
Oh, you're flying.
Yeah, our team members.
Arnav will be there. So many of us will be around there. We're showcasing a couple of other things at the Microsoft booth, but we should have one of the kiosks there specifically talking about both the Open Academic as well as the instance of our web service that showcases some of that data being fed live. Yep. All right. Well,
here's the commercial right here.
That's right. You got in the final plug. And on that note, just to round out the day, we do have some postcards up here, and we'll have them at the booth as well. We are introducing some new features over the coming months, and if you come by the booth, we'll actually give you a QR code that you can scan to get an access code to the website. You'll be some of the earliest adopters of our new site, be able to log in, create an account, give us feedback on some of these features as well. And we are developing some social features on the site, so allowing people to make comments on papers, on conferences, on people, to like and to follow and get a personalized feed. But the important point of this from a data aspect is that data, that social data, is also going to be going into this open academic data set, along with the A minor data as well. So this is an area where this becomes nicely recursive and self-fulfilling, in that the data that we generate from the user experiences on the site will also be data that the research community can start playing with once we have enough to feed back into it. So thank you all very much. It's been a great day today. In less than 30 minutes is going to be the opening ceremony this evening. Come and join us for that when we actually hand out the final award checks for the first, second, third place, as well as for the phase 1 and phase 2 winners. So thanks, everybody. I appreciate it.
Thank you.